My name is Yuhong from Fudan University. Today, I will present our work on the new approach for sensitive data discovery in mobile apps. This is joint work with Indiana University Bloomington. Okay, so nowadays, mobile apps often integrate many existing web services for enriching their functions. However, such functionality comes with significant privacy implications. As previous studies showed, such integrated services not only have the ability to collect different sensitive data without user consent, but also are capable to associate users' different activities together to infer other secrets. Let's take the following case as an example. Here, a popular news app integrates a library for sharing posts to different social networks, as we call it the sharing syndicator. When users sharing news in this app to her social network, she will not know that this process is actually handled by a third-party library, and her login credential, like access token, will be used by this library for delivering posts. What's more, we found that using the acquired access token, this syndicator also collects all users' available sensitive data, including her detailed profile, together with the shared content to its own server. Motivated by this case, it is very necessary to understand the scope of this problem with an in-depth study at a large scale. However, to find information leaks in such scenarios, the first step is to identify the sources of such sensitive data. For the automated privacy leakage analysis, traditional sensitive sources Okay, let's go. Traditional sensitive sources are actually labeled by a set of fixed APIs that refer to system-controlled privacy. To expand the scope for detecting privacy leakage in fine-grained settings, recent research also provides solutions to identify user input data. However, the more complicated case is user-sensitive data from app server side, especially after she logs into her account and download data with the server. In this case, either UI or system API-based labeling approach are unable to effectively locate sensitive data, because regardless of their sensitiveness, loading such information always goes through generic system APIs with basically the same characters. One may also consider capturing such data by intercepting network interface with runtime analysis. However, this is also not practical for automated leakage analysis, since modern apps always require complex login conditions to trigger the real network traffic. A key observation in our research is that most apps today contain a large amount of semantic information in their code for supporting software development and maintenance. For example, program elements like method names and variables are often given meaningful names with plain text to explain other related content, such as the value of a certain key. This provides us the opportunity to discover sensitive data from app side rather than analyzing the real network traffic. Based on this observation, we first developed ClueFinder, a novel technique that mines app code to recover semantic clues for identifying sensitive information. The design of ClueFinder, covering not only those sensitive data labeled by system APIs and user interfaces, but also server-side private data. Then, armed with more sensitive data sources discovered by ClueFinder, we are able to evaluate the exposure risk of such sensitive data among 445K apps. The results enable us to gain new insights about how private data is accessed by different third-party libraries at a large scale. Although app code is semantics rich, recovering truly sensitive data sources from the code is not easy. The first challenge is how to effectively solve various ambiguity of text strings in app code. As shown below, in many cases, the presence of a sensitive keyword may not represent any sensitive content. Secondly, program elements that carry sensitive tokens may not carry sensitive content by themselves. For example, a log information with error message, or an API for setting string labels into its user interface, both of which do not carry sensitive content. Here, we present the design of ClueFinder. It includes a semantic locator, a semantics checker, a structure analyzer, and a leakage tracker. The idea behind ClueFinder is to quickly screen across the app code to locate privacy-related tokens within program elements, and then semantically evaluate the program elements to drop false positives. For a given Android app, Semantics Locator first disassembles its code and identifies the program elements that carry sensitive tokens. These sensitive elements are then inspected by the checker. The checker uses NLP techniques to determine whether identified tokens are indeed the main subject of each element. These program elements meeting the requirements of semantic checker will further go through a program structural analysis. The structure analyzer classifies each function invocation statement as either sensitive or not. Lastly, the reported sensitive elements are delivered to tracker. The tracker then traces the propagation of sensitive information. Now we come to the detailed explanation for each module. To identify privacy-related data through the semantics of program elements, we first gather 35 privacy items from multiple sources as the knowledge base. Then, the semantic locator takes all possible program elements with semantic information into consideration. These elements include method names, variables, and more importantly, the constant strings in parameter for each statement. The goal of semantics checker is to perform a grammatical analysis over such privacy-related tokens and filter out the method terms, the matched terms that are not serving as the theme of their semantic context. We use typed dependency parsing to check if the privacy-related keyword shares a specific relation with other words. The typed dependency parsing provides a simple description of the grammatical relationships in a sentence. Therefore, it provides a more structured format to analyze the sentence. Consider the following negative example. In this method name, the location only holds a compound relation with update and time, where the main subject of this term is to get time interval, indicated by the direct object relation between the term get and interval. So the method name does not indicate any existence of location data. Taking another example here, the keyword phone only holds a percentage nominal modifier relation with term mine. The direct object relation here is between design and T, thus indicates the term is not actually describing someone's phone number. However, after the above analysis, even when a sensitive token plays a central role in the name of a variable or a method name, such program element may not necessarily relate to private content. For example, the first statement in red only returned a Boolean value indicating the existence of a specific key name. And the last statement in red only reports a message indicating location information has been updated. On the contrary, both the second and the third statement indicate the existence of sensitive data by either its return value or its parameter variable. Then, the structure analyzer to filter out those irrelevant statements. The structure analyzer employs a SVM-based classifier with a set of program structure features to determine whether a given program statement indeed touches private user content. Specifically, we chose the following features, including the method name, a class type of the parameters, return values, and base values, as well as the constant string, constant variable patterns. Our key observation is that when labeled elements are involved in data read or write operations, almost always the operations are related to sensitive information. Leveraging this observation, our approach looks for evidence where such sensitive data operations indeed take place. In the Leakage Tracker, the statements together with privacy-related semantics are treated as the actual sensitive sources for detecting information leakage. Leakage Tracker extracts data-typed objects within statements from their parameters or return values and then perform a data flow-based data analysis on these objects. Since it is unable to get a ground truth for evaluating the overall effectiveness of ClueFinder, our manual validation over 100 randomly selected popular apps show that ClueFinder achieves a 91.5 precision in identifying privacy-related content. The main false positives in ClueFinder are caused by the insufficient semantic analysis for locating sensitive data. As an example here, in this statement, ClueFinder will consider variable R1 to contain access token, which is actually being stored in extra places. We believe such false positives could be improved by employing more advanced NLP analysis techniques. For false negatives, some cases were not covered by our label training set. For example, the gender represented by the integer value. Such limitation can be further improved by employing more training data for the classifier. Here, we will talk more about the limitation of our approach. The design of ClueFinder is limited to deeply obfuscated code if all semantic information were removed from the decompiled app code. However, this does not mean ClueFinder cannot tolerate any obfuscation. This is because even with moderate code obfuscation, semantic information is usually preserved in some critical locations. For example, the system-level code structure features like parameter types and return values cannot be obfuscated, and they can still be leveraged as features by ClueFinder's classifier to determine the presence of sensitive data. Besides, due to practical constraints in code obfuscation, those methods related with reflections and the interfaces of third-party libraries usually will not be obfuscated to make sure developers can easily integrate them into their app code. Actually, we found that only 11.3% of statements were obfuscated in our testing dataset. Now we come to the large-scale measurement over 445K apps. In our study, we crawled apps from either the official Google Play market and a third-party app market in China. Note that in this study, instead of detecting privacy leakage to network, we looked for leaks of sensitive user data to third-party libraries from apps themselves. This is because once an untrusted library obtains private data, it often can manage to send data out through covert channels without getting caught. Among all apps in our dataset, ClueFinder discovered around 26% apps leaking private user data. Note that here we just focus on findings related to source missed by prior approach. As a result, traditional system-controlled sensitive sources are already being excluded from our statistical result. From the ways these libraries interact with their hosting apps, we summarize the leakage patterns into the following different types. First, as shown in the motivating example of ClueFinder, some third-party libraries deliberately harvest information from apps. These sensitive data could be leaked out even without developers' attention, not to mention users' awareness. Interestingly, we also found that developers give private information from apps through the API interfaces of third-party library, which intended to disclosure and overshare users' private data. As shown in the following case study, in the popular dating app, we found that each time users seeks for a nearby dating target by refreshing the user interface, This app will directly send users location, bio information, and dating targets to a third-party library named AppBoy. All such information disclosures are unknown to user. To conclude my talk, in this work, we proposed a novel technique for identifying user-sensitive data. This technique helps us to extend the scope for labeling more private sources from app code. Also, we conducted a large-scale measurement about privacy exposure risks to third-party libraries and give a set of findings to highlight the importance of data protection in today's software composition. Okay, that's my talk. Thanks.
So we have time for a few questions.
So I'm Nina Taft from Google. Thank you. That was a very nice talk. And I like your work with using NLP to do the analysis of the privacy tokens in code. That's a very nice idea. I do want to suggest, though, that the use of the word leakage is a little misleading here. That there's no doubt that this data is going off the phone and is being disseminated. But if users have agreed, like through the permission system, to share their location, then it's not a leakage in the sense that there's nothing illegal going on. There's nothing improper going on. The users have agreed to it. So the information's flowing, but it's actually all been properly, from a legal point of view, agreed to. So the word leakage implies there's something wrong going on, and that's why I think it can be misleading. It's a tough term.
Okay, yeah, so thanks for your suggestion.
Okay.
Thanks.
Other questions? So let me quickly ask one. So I wonder how robust your techniques are to, for example, other languages or different programming style, because it's based on natural language processing, and if they have a different language system or different grammar, what kind of impact that will create on?
Okay, I think actually the type of language will not greatly affect the precision, like the effectiveness of ClueFinder, as long as there exists semantic information. For some type of non-type programming language like JavaScript, that might be affect the ClueFinder's effectiveness, but maybe like C++, Java, and all these are very okay. Yeah.
Okay, thank you. Any other question? If not, let's thank Yuhong one more time.
Thanks.